Hello everybody, welcome back. Hope it's bright enough. Let's get going on section 7.4. This is a convoluted section. It's a long one. Under normal circumstances, this would be the most intricate section, the one with the most detail. And we'll have 3, maybe even 4 videos in section 7.4. And what it's called is, there's a lot of words here, but we're going to approximate the binomial distribution. Am I right? No, that's sure. Binomial distribution. Oops, I'm going to abbreviate. Using the normal distribution, and that's what it's called. So just go back to recall binomial. This is section 5.2, distribution. And this is section 5.2. And the first, no, not the first, I think the second and third problem on your quiz were binomial distributions. It'll be on the final. And so will this section. Recall the binomial distribution. One, there's 4 components of this. There's independent trials. There's n of them. That n's going to become important. Each trial is, there's 2 outcomes. Either a success or a failure for each one, either a yes or a no. The probability of success we call P. One minus P failure. 1 minus P is failure. And x, then there's the random variable x is the number of successes. S-U-C-C-S. And if this is so, if we use the binomial theorem, for example, suppose probability of voters overall is 60%, and we have 15 voters. What is probability of 11 of them voting? Well, we did this. Then if that's the case, then the binomial distribution, probability x is 11. I'm going straight to the example. It is a combination from n, the x that we want, times the probability of anyone voting, 0.6, times the probability of people not voting, raised to, in this case, the 4th power, the number of people that aren't voting. And we came up, I did this, 13%. Of these 15 people, it is 13% likely that 11 voted. Okay, so that's the binomial theorem. And now, that's not very powerful because of, for one thing, we're talking exactly 11. Right? That precludes 12, 13, 14, 15. That precludes 10, 9. I mean, exactly 11. And 2, it's 15. N is 15. Well, suppose, this is more helpful, N was 150. We're going to take 150 voters. Of these, determine probability that 110 of them voted. And note it again, that's exactly 110. It's not 111, not greater than, less than, equal to, which doesn't help. It's not helpful. It will be when we use the normal curve. So this is the probability x is 110, is a combination from 150 to 110, 0.6 to the 110, 0.4 to the 40. These numbers are huge. My calculator can handle them. Your calculator can probably handle them, but hey, the bigger they get, the worse it's going to be. Your calculator can't handle this. Is this the one that's absolutely dead zero? Oops. Yep. This, the probability of this is 8 times 10 to the negative 24th, which means there's a 0.024 of them babies before the first significant digit shows up, which means it's literally 0. And if you think about that, you know, we're talking about exactly 110 out of 150. That just doesn't make any sense. So now try of 150,000, 110,000. And of course it's going to be way 0 because you're talking exactly. How about at least? Well, if you try this with 150,000 and 110,000, there's 0 chance your calculator can use this. If you think about what it is, it's a Pascal's triangle. You have to go to the 150,000th row of Pascal's triangle and then the 110,000th entry there to find out what that was. This, 0.6 raised to the 111,000, whoops, that should be a 10, but, is completely off the charts. So this is off the chart. And so we're going to, let's just do these. There's a way to, because of the central limit theorem, because of the central limit theorem, whoops, because of, the central limit theorem, please, it's a theory, doesn't really matter what it says, but because of that theorem, we can use the normal distribution to approximate this. To approximate the binomial. Okay. And first off, when you use the normal distribution, it doesn't matter. It doesn't make sense to do it exactly. So we're always doing at least. And you can do this. We're going to stop pretty soon. There's a lot more coming. You can do this if n times p is greater than 5, and if n times 1 minus p is also greater than 5. And I want to talk about what n times p is in this example over here. And please note, n times p is the mean. I mean, right here we have, right there, we have 60% of 150 people. N is 150. P is 0.6. N times P is 90. We are going to be drawing a curve that the mean is 90. And then really, what are we looking for? 110. There's 110. We're going bigger or lesser, depending on which way, depending on what the problem says. We'll get back to that in just, that's the introduction. We'll get back to the specifics next time. Hopefully this is helpful. See ya.